Hey, and welcome. Today, we're going to peel back the case on our favorite gadgets to find a real unsung hero. It's this invisible tech that stands guard, protecting our devices from the elements day in and day out. Let's dive right in. You ever stop and think about that? I mean, seriously, we take our tech everywhere. Out in the rain, into super humid gyms, near the salty ocean air. So how in the world do these complex electronics survive all that without just short-circuiting into a useless paperweight? Well, the answer lies in a microscopic battle being fought on their circuit boards.
And at the heart of pretty much every electronic device is one of these, a printed circuit board, or PCB. You should think of it as the central nervous system for your tech, right? It's got all these delicate copper pathways connecting all the critical components. And while they're absolutely brilliant, they are also incredibly vulnerable.
And that brings us to the villains of our story. You see, there's a whole bunch of invisible threats that are constantly attacking these sensitive circuit boards, especially when they're being used outdoors. So the main culprits are actually things we run into all the time. Moisture is the big one, obviously, but salt fog, from coastal areas or winter roads, is also unbelievably corrosive. Even something as simple as dust, or extreme heat and cold, and chemical fumes in industrial areas, they can all cause some really serious damage. So when these attackers, especially moisture, get onto a PCB that has power running through it, this really nasty process called electrochemical migration can start. Now, I know, it's a bit of a mouthful, but the concept is actually pretty simple. Tiny metal ions start moving where they shouldn't be, and they form these unwanted little bridges between the copper pathways. And the result? A short circuit and, well, a dead device. So, how do we fight back against this? I mean, we can't exactly wrap our circuit boards in plastic wrap, right? The solution needs to be way more elegant and effective. So, enter the hero of our story, a microscopic suit of armor. And this hero is called a conformal coating. It's a super thin layer of a polymer material. You can kind of think of it like a liquid plastic that's applied over the entire circuit board. It perfectly conforms to the shape of every single tiny component, and that creates this seamless, non-conductive shield that just seals out all those environmental enemies. But here's where it gets really interesting. Just like you'd choose different armor for different kinds of battles, engineers have to pick the right type of conformal coating for the job. Because, you guessed it, not all shields are created equal. So let's look at the two most common types. First up, you've got acrylic coatings. These are the versatile all-rounders. They're easy to apply and, this is crucial, they're easy to remove, which makes repairs so much simpler. They're great for your everyday consumer electronics. But for something a bit more extreme, like the electronics under the hood of your car or inside an aircraft, you're probably going to need silicone. It's incredibly flexible and it can handle these wild temperature swings without cracking. Now, what's really fascinating about this chart is how it shows you the trade-offs involved. Just look at urethane for a second. It's got excellent chemical resistance, which is perfect for industrial settings, but it is very difficult to repair. Or synthetic rubber, it's super flexible, just like silicone, but again, good luck trying to repair it. And this is the key point. Engineers have to balance performance with the realities of manufacturing and maintenance. There is no single best coating, only the best one for a very specific job. Okay, so you've chosen your champion based on the specs, but how do you really know it's strong enough? You can't just cross your fingers and wait for a customer's phone to fail on a rainstorm. You have to prove its strength. And that means sending these coatings into the electronics torture chamber. The first trial is the humidity test. In this one, coated boards are placed in a chamber that cycles between high heat and nearly 100% humidity for over 130 hours straight. Yeah, it's basically mimicking a lifetime of exposure to damp, sticky conditions. Next up, the salt fog test. This one simulates the absolutely brutal environment of a coastline or a salted winter road. A corrosive, salty mist is just blasted at the boards for days and days to see if the coating can stop rust and electrocorrosion in its tracks. And finally, maybe the most brutal of all, thermal shock. Here, the boards are rapidly moved from a freezing chamber, we're talking minus 40 degrees Celsius, to a scorching hot one of 150 degrees, over and over and over again. This whole thing tests if the coating is going to crack under the extreme stress of all that expanding and contracting. So what does success actually look like? Well, it looks like this graph right here. It's showing the voltage across a circuit during one of these tests. You see that perfectly flat, stable line? That means zero moisture is getting through. The shield is holding. The insulation is perfect. This, my friends, is a win. And this is what failure looks like. Just look at how the voltage plummets to zero almost instantly. That's a catastrophic short circuit. The shield has been breached, moisture got in, and the device has completely failed. Game over. But here's a really key insight from the engineers who do this stuff for a living. A coating might pass a simple humidity test, but that's not the whole story. As this quote points out, real-world failure almost never comes from a single enemy. It's from a combination of them. The absolute worst damage happens when moisture, temperature changes, and contamination all team up. And this brings us to the final, and maybe the most critical part of our story. If it's not just about picking the toughest material, what is the true secret to winning this microscopic battle? What's the one detail that makes or breaks the shield? It all comes down to a concept they call sharp edge coverage, or SEC. And it's a really simple idea. A shield is only as strong as its weakest point. For these coatings, that weak point is almost always the sharp corners of the components on the circuit board. Okay, let's look under a microscope to see exactly what I mean. This is a component coated with polyurethane. Now, on the flat top surface, the coating is a very healthy 135 micrometers thick. That's more than the width of a human hair. Looks perfect, right? The shield seems strong. But now, let's zoom in on that sharp corner. This one image explains the entire problem. The coating thickness has plummeted to just 19 micrometers. That is 4 times thinner than a typical piece of paper. And why? It's just simple surface tension. It caused the liquid coating to pull away from that sharp edge as it dried, and that creates this tiny, almost invisible weak spot, a real Achilles heel where moisture can just break right through. So the most important takeaway here is this. Winning isn't just about the material. It's all about the application. The most advanced coating in the world is going to fail if it's too thin on a sharp edge. The real secret to a truly invincible shield is combining the right material with a flawless application process that guarantees consistent thickness absolutely everywhere. So the next time you check your phone in a drizzle, just take a second to think about that invisible shield holding strong, fighting off the elements on a microscopic battlefield. It's all thanks to the science of conformal coatings. And it makes you wonder, what other invisible battles are being won inside the tech you use every single day?